Hello everyone. Do you guys hear my voice? Yeah. Today my microphone doesn't work well, so I think I have to use this microphone. Um, like I already announced in the beginning of today's lecture, we are going to talk about the research project a little bit. So I know some people have some difficulties in doing some problems. So let me talk about them first. So I think the number one is easy. Just obtain summary statistics, and then make a histogram for the variable wage, and you need to make another histogram for education because we want to see the relationship between education and wage, and these two variables are important. So you are asked to make these two histograms. So you guys know how to get a summary statistic, right? In Stata, you can use just summary, or so let me. Yeah, in Stata. So basically, you can use this command in Stata to have summary statistic. But if you want to have summary statistics for particular variables, then right after this command, SU is for summary. Right after this command, SU, you can list the variables. Like for example, in this case, you can give wage. Right? Then Stata is going to calculate sample average, standard deviation, and minimum value and maximum value, and the number of observations, things like that. So the first problem is super easy. Actually, the first problem is supposed to be very easy, so I don't think this is a problem. And then question 2, you are asked to estimate the linear regression. You're going to regress wage on education. So this is a simple linear regression. Here, what I mean by simple is the regression with only one random variable on the right-hand side. One thing that you have to keep in mind is you need to calculate robust standard error. I assume everybody knows how to do this, right? So I'm not going to go over this part. And the question 3. So here you have to calculate residuals. Residual is the difference between the left-hand side variable and the predicted value of the left-hand side variable. So as you see in the problem, residual is defined in this way. Yeah, so residual is defined in this way. You can calculate residual using the estimated slope and estimated intercept. There's another way to do that. But here, let me introduce. Actually, I already discussed about this through the course web page, right? If you use predict, the command predict, then there's an easier way to calculate residual and also the fitted value. So let me show you this. Yeah, this is the command in Stata. So if you use predict, then you can calculate residual or fitted value. So using predict, we can do two different things. One is computation of residual, and the other one is a computation of predicted value, fitted value. So we need to use the option. So right after predict, you have to write the name for residual or the name for fitted value. So for example, right after predict, I'm going to use this name E hat. So when I compute residual using Stata, all those residuals are going to be stored in variable called E hat. E hat is the name that I choose. And then I need to give option. Right after the name, the variable name, we need to give comma, and then RESID. So that is for residual. So after comma, if you put RESID, then Stata is going to compute residuals. But you have to do this right after you run the regression. So if you do this before you running a regression, then you will have some error message. So you run regression first, and then implement this command. If you want to calculate fitted value, then you need to have different name. Like, so again, predict, and say y hat. Now I'm going to use y hat to store all the fitted values. Y hat is the variable name that I chose. And then after comma, I put option xb. So xb is the option for fitted value. So using these two different options and using this command, you can calculate either residual or fitted value. Then this question number 3 is going to be easy. And I assume that you guys already know how to make scatter diagram. So you have to use command two-way, and then you need to choose the type of diagram. In this case, that is a scatter. And you put x variable first, y variable first, and then x variable later. Then you can generate a scatter diagram that gives you some idea about the joint distribution between residual and education. Then from this diagram, you can say that whether homoscedasticity assumption is reasonable, or you have to use robust standard error, things like that. Okay. And number 4 is just a repetition of the regression analysis for 3 different groups. Using if, option, you can select sub-sample of the data set that you have. So, for example, in the data set, if you run the regression only for male group, then right after if, you choose variable name female and set it equal to 0. You need to put two equal signs like this. Then you select sub-sample with male individuals. Then you can get a regression result only for this subgroup. If you look at the previous solutions, the solutions to the previous tutorial problems, then you should be able to find some of these you should be able to find some examples where you can learn how to use this option. Okay, so answer for question 4 can be long because you have to repeat the same thing for 3 different groups: male, female, and also black people. But basically, once you know how to do this computation for one particular group, then you can just repeat the same thing again and again. And question 5 seems to be the problem, right? So on the left-hand side, you still have wage. And on the right-hand side, you have, what is this, education, square. So you need to generate new variable using command gen. So use generation in data. And in my case, I can use this name, edu2. So I'm going to use this new variable for education square. And then you can define this variable, right? So I'm not going to give you the whole answer. But again, if you look at the solutions to the previous tutorial practice problems, then you can see how you define new variable using generate command. Okay, and then you regress wage on education square, including constant, right? So this is not a big problem. And then marginal effect. Marginal effect, there are 2 different ways of calculating marginal effect, but let me introduce one of them, actually the better one. Yeah, so suppose we have this regression equation. This is a population regression equation, right? So suppose X is education and Y is wage. And we have data, so we can run regression. We can regress Y on X so that we can have OLS estimate for alpha and beta. So once we have OLS estimate for alpha and beta, then we can use alpha hat and beta hat. They are OLS estimates. Once we have alpha hat and beta hat, then we don't have residual anymore, and the left-hand side is going to be the fitted value, right? So then, at a certain value of X, you can have prediction on the left-hand side variable using your estimate, right? Which means, so, conceptually, let's start some number X. We didn't choose the exact number for X. Just, suppose we have a number X. And then we want to increase X by 1 unit, right? So then, X right? So we can calculate the first line, and also we can calculate the second line. Second line is going to be different from the first line. That the second line is not exactly y hat, right? Because we evaluated this right-hand side equation at x plus 1 instead of x. So let's put this. Say y tilde. Yeah, say that is y tilde. Then marginal effect is y tilde minus y hat. Okay? So computation of marginal effect is that simple. run the regression and using the numbers from the state outcome, you can choose the numbers for alpha head and beta head because there's an estimate for intercept and an estimate for the slope parameter. Then instead of X, you can use education, and instead of Y, you can use wage, right? Then forget about the notation on the right-hand side, left-hand side, Y hat and Y tilde. Just, you know how to compute this. This is nothing but multiplication and addition. And you know how to do this, right? Then just take difference between these two. Subtract the first line from the second line. Then that is marginal effect. So here, we increase education by 1 year. 1 year. Then the difference is what's the effect of increasing education by 1 year on the expected income, expected wage. That is the thing that we want to have, all right? We added 1 year like this. This kind of exercise is allowed because education is discrete variable, right? Education in our data takes values on like 12, 13, 14, 15. In this way, education, the support of education is a subset of positive integers. This is not a continuous variable. But if X is continuous variable, then the marginal effect should be obtained in a different way. Yeah, if X is continuous, then the marginal effect is derivative of Y with respect to X. Marginal effect can be written as derivative of Y with respect to X. So when we change X just a little bit, what is changed on the left-hand side variable? That is what we want to capture by calculating this marginal effect. When X is discrete, you can still calculate this derivative. But in that case, the marginal effect that you find by taking this derivative is just approximation. That is not exact marginal effect when X is discrete. You can do this only when X is continuous. Maybe if you have time, you can try both of them. And you can see the quality of approximation of using derivative for the discrete regressor. All right? Any questions so far? All right. Then question is.
Regarding measuring marginal effect, should we take X as an arbitrary number or as a number from?
So your question is how can we choose? This number,
yeah.
X, right? In the
Do we have to take it from the data set or any arbitrary?
hold on. This is number five, right? Yeah, right. So you are asked to calculate the marginal effect at 12 years of education and 14 years of education. So the value for X is given in the problem. Okay? If the value of X is not given in the problem, then you can just give formula. Okay? So in this case, the formula marginal effect is hold on, please. Yeah, right. Yeah. Y tilde minus y hat. But there's one thing that you have to be careful. In this example, in this problem, you are not using education itself. You are using education square, right? So the computation can be a little bit different. Here, x is education square. So you put square here, and you put square here, right? Instead of education, you are using x square. And instead of x plus 1, you have to use x plus 1 square, right? Then marginal effect is going to be x beta hat x plus 1 square minus beta hat x square, right? So this is the formula for marginal effect in this particular problem. If the functional form is different, then you are going to derive different form of marginal effect. Any other question about question 5, problem 5? Yeah. Okay. Now, question 6. I think many people have some problems about question 6, and hold on, please. I understand this problem is a little bit more difficult than other problems. So let me explain how to make the diagram. So previously we regress education. We regress wage on x square, right? Then using predict command, we can compute fitted value for this quadratic regression, right? Say use predict. I'm going to define new variable y hat 2, and after comma, I will compute fitted value, right? And then when you draw regression line for this regression, the way you compute this is to use QFIT, quadratic regression, and using quadratic regression, we're gonna fit the data, right? And then instead of y variable, you have to use y hat 2. And then education, right? So actually, the data comment line is longer than this. This is part of that line. So in the beginning of this line, you have to start with two-way, and you are supposed to generate scatter diagram of the data, and then you're gonna put linear regression, the estimated regression line on the data, and then you're gonna do this. All right. So you will have scatter diagram, and you will have two estimated linear regression. One is linear, and the other one is quadratic. Okay. Question? Okay. So by doing this, y hat 2 is going to be the fitted value of the second regression estimation, right? So that is going to be, if you calculate the fitted value, then the scatter diagram is going to be, By the way, you are not asked to generate this scatter diagram. You are asked to generate scatter diagram of the data. But suppose we want to generate the scatter diagram of fitted value and education. So here, we're going to put y hat 2 and education. Then because y hat 2 is the dots that are on the regression equation, quadratic regression equation, the shape should be something like this. It is going to be very different from the data. And then, using this command, qfit, we're going to fit y hat 2 using education. Then, obviously, the estimated regression line using this data is going to be exactly connecting these dots, right? So that is why we have to use y hat 2, the fitted value, instead of the data. If we use data, so if we use qfit wage and education, right? Then the scatter diagram must be something like this. This is the real data. Of course, the real data should look different from this one, but suppose this is the real data. Then qfit is going to estimate the usual form of quadratic equation. Then that will be something like this, and this is going to be different the previous one. The reason is because if you just do this, then this estimated line is going to be associated with y is equal to alpha plus beta 1 x plus beta 2 x squared plus u. So here we have one more polynomial term. That is the difference. Again, if you generate a line using this command, putting wage, the real data, right after qfit, then what you are doing is you estimate this equation first. You estimate this equation first, then you draw this prediction line. But in the problem, what we have is we have different equation where beta 1 is assumed to be 0. So we don't have this term, right? We have only a second order term. So what we estimate is different from just usual quadratic equation. So there's a little bit of difference. Did I answer to your question? Okay. Any other question? Okay, that is pretty much it. You know, I am not supposed to give you all the answers of your homework, so let me stop here. And if my explanation is not clear to you guys, then you can stop by my office. After today's lecture, my consultation is between 12:30 and 2:30. Okay, so now we spent 30 minutes of time on this homework. Actually, my plan was to spend like 10 minutes of time to this homework, but it turns out that I spent more time. All right, so today, so until last week, we discussed about a very simple empirical environment where we have one left-hand side variable and one right-hand side variable. We regress left-hand side variable on that regressor. Now, we're going to generalize our situation to a little bit more complicated situation where you have more than one regressors. So here the chapter title is linear regression with multiple regressors. But the idea is about the same as before, and I can say that the additional complication is very minimal. So you don't have to be worry about the difficulties too much. If you understand the materials so far, then the material in this lecture is going to be straightforward. So what we are going to do is we want to study omitted variable bias first. And then we will talk about causality and regression analysis. Then we will discuss about how to come up with multiple regression and how to calculate OLS estimator. And we will talk about measures of fit. Then sampling distribution of the OLS estimator. We need to have sampling distribution because we want to conduct statistical inference, right? Okay, so in population regression equation, we have to put error. We use notation U because when we explain two different variables, they are moving in a different, many different complicated ways. So the reason is because having only one variable, we cannot perfectly predict the left-hand side variable. There must be some omitted factors, variables that influence the left-hand side variable. But many cases we cannot include all of those variables. There must be some omitted factors, and those omitted factors are included in the error term. There is an error term. All regression exercise, we must have error term. But sometimes having error term is fine, and that is so natural. But some other times, omission of some variables can lead to bias in the OLS estimator. So under what conditions do we have omitted variable bias? The bias of OLS estimator that is caused by omitted variables is called omitted variable bias. The name is straightforward. This is bias because of the omitted variables. That is called omitted variable bias. Actually, we're going to have omitted variables all the time. It is likely that we will have omitted variable bias. But only when those omitted factors satisfy the following two conditions, we will be in trouble. So two conditions for omitted variable bias. The first one is, say Z is another factor that is omitted in our regression equation. Z has to be a determinant of the left-hand side variable. We're going to see an example about Z. So if Z is a determinant of left-hand side variable, then Z is a part of U. So the first sentence is equivalent to the sentence inside of the parentheses here. And the condition 1 itself is not a problem. Condition 1 and condition 2, these two are satisfied, then we will have bias. Z is correlated with regressor X, the variable that is included in our analysis. If omitted variable is correlated with included our regressor, then we will have bias problem. Our OLS is going to be biased, and that is not going to be consistent. So we cannot have correct estimate even when we have super large sample. So we need to fix this problem somehow. So this lecture we will talk about that, and next few lectures we will discuss about how to fix this problem. So let me give you an example first. So let's go back to our previous example where the left-hand side variable is test score, and on the right-hand side we had only one variable, that is STR, student-teacher ratio. Now, think about English language ability. So in California, there are many communities with people from outside the country, right? So for some district, students have to learn English. If they have lower English language ability, then it should affect standardized test scores because the standardized exam must have English as a subject, and also all those problems are written in English, right? So English proficiency, we can think of it as one determinant of the test score. So in this case, Z is the notation for English proficiency. And Z is obviously a determinant of the left-hand side variable Y, which is test score. Another way to say that is Z is part of our error because Z has influence on the left-hand side variable, but Z is not included in our regression analysis. That means Z is a part of the error term. And I want to argue that this Z, English language ability, is correlated with student-teacher ratio, the X variable that is included, because immigrant communities tend to be less affluent. You know, many people are coming from Mexico, and they are poorer and compared to other communities. Then they have smaller school budgets, therefore they will have higher student-teacher ratio. So we can argue that Z is actually correlated with X variable, the student-teacher ratio. So if this story, the story in the second, number 2 is correct, then we will have biased estimate. Beta 1 hat is biased. Then question is, what is the direction of the bias? Actually, thinking about this story, we can figure out the direction of the bias. We can say whether the OLS estimate is underestimated or overestimated. We can figure it out. We will see that soon. So suppose the true model is given in this way. So left-hand side is test score once again, and we have constant beta 0, and beta 1 times student-teacher ratio, and the beta 2, which is additional term, that is multiplied by Z. In this case, that is English proficiency, right? But unfortunately, we don't have Z in our regression equation until last week. Okay, so let's assume the following stories are reasonable. We don't know whether the following story is really reasonable or not from the data, but theoretically, maybe the following story is going to be quite convincing. So think about student-teacher ratio increases. Then one teacher has to deal with many students. Then students' performance will go down. Test score will go down. So before running this data analysis, we can imagine that the true value of beta 1 is negative. It is not positive, it is negative. This is our theory. And suppose to think about the situation where English proficiency is getting better. Sorry, what is that? English ability. Yeah, Z. Z is the ratio of students who are learning English as a second language. So for a certain district, if Z is higher than other district, then that means on average in that district, English skill is lower than other language. Then for that district, we can expect that test score is lower than other district. Z is a part of error, and in this case, because high Z causes lower test score, we can imagine that beta 2 is also negative. Now, we go down to the regression equation that we estimated. We estimate this last regression equation without having Z. In this case, U is included. U includes two terms, beta 2 times Z and additional error term, right? Then when we regress test score only on student-teacher ratio, then the effect from Z will be observed, our estimate on beta 1, right? So because test score and student-teacher ratio are correlated, the effect from English ability is going to be observed, our estimate on the slope parameter that is attached to STR. Which means our estimate is capturing not only the effect from student-teacher ratio, but only effect from lower language ability. So, which means we are overestimating the effect from student-teacher ratio, right? Okay, so let's look at this this data. Actually, in the original data set, we have information about the percentage of English learners in the district. Okay, so let me use this mouse pointer. So the first column is subsample of small class size, the districts with small class size. The small class size is defined as class size less than 20 students for one student. And the second column is those districts with student-teacher ratio greater than 20. So here, including all these districts, we compute the average score that appears over here. And for the this first category, the number of sample is 238. We did the similarly over here, right? And then the difference is 7.4. Actually, in the last week, we obtained this number by regressing the test score on dummy for the small class size. And now, these are the columns. So this is one way to divide the sample into two different groups. One group has small student-teacher ratio, and the other one is large student-teacher ratio. And now, look at this row. So here, 1.9% means we collect all the subsamples. We collect all the school districts for which the percentage of English learners is less than 1.9%. So we are collecting school districts with mostly native English speakers. And that is the first row over here. So in terms of percentage of English learners, this group is pretty homogeneous. There's no difference in terms of the English proficiency for this. The sample appears on this line. Only difference is within this subsample, some districts have smaller student-teacher ratio, and some other districts have larger student-teacher ratio. Now we have more categories for percentage of English learners. The second group, the percentage is between 1.9% and 8.8%. And the third one, we increase the percentage a little bit. And the last one is the districts with largest percentages of English learners. So the idea is for each line over here, each row, only difference is the class size. For each row, there's no much difference in terms of English proficiency, right? And then for those districts with mostly native speakers, when we take the difference of the difference of test score between small class size and large class size, then the difference is even negative, right? So the test score for small student-teacher ratio is 664.5, and the larger student-teacher ratio is 665, and the difference is even negative. Of course, the standard error is also large, so we cannot say that this is statistically significant. And the second group, the percentage of English learners is between 2% and 9%, roughly speaking. And now for this particular subgroup, the effect of having small class is 3.3 on the test score. This is positive, but very small, right? And the third group, the effect is 5.2, and the largest group, the effect is close to 2, right? None of them is smaller than 7.4. So if we aggregate all the population, then looks like the effect of having smaller class size on the test score is 7.4. But if we control for the percentage of English learners, then the effect tends to be much smaller than this one, which means the percentage of English learners really affects the left-hand side variable, which is test score, and that is correlated with student-teacher ratio. Okay, so let's use this notation, percentage of English learner for this variable. Okay, so this is something that I already yeah. Okay, so then the discussion so far raises another question. How do we define beta 1? So when we regress this one, we had beta 1. And on the top of this slide, we have another beta 1, right? The definition of the beta 1 in the first equation is going to be different from the definition of beta 1 in the second equation that doesn't have this additional component. So what is the real definition of beta 1? And another way to ask this question is, what precisely do we want to estimate when we run a regression? So roughly, there are three possible answers to this question. The first answer is we have the data distribution, and we want to draw just one straight line that explains the relationship between variables. That is one possible thing that we can do by using regression analysis. However, this can be useful sometimes, but this is not interesting intellectually, and it is not the course is about. You can do this if you want, but in economics, mostly we are not interested in this kind of exercise. By doing this, we can have some idea about statistical association between two different variables. However, using this, we cannot answer to any policy questions. So we are not interested in this exercise. And the second one is we can make forecast. We will do this kind of exercise when we have time series data. Without having a causal effect, interpretation of causality, we can still predict the left-hand side variable using the right-hand side variable when we have regression methods. The last one, we want to estimate the causal effect on y of change in x. when we change x, we want to see what's the effect on the left-hand side of the variable. That is what we are interested in. We want to see the policy effect. So, for example, suppose the school decide to cut class size by 2 students. Then what would happen on the test score? This is the kind of question that we want to answer. This is a causal question, right? This course is mostly about this kind of problem until the chapter right before the time series. So for time series, we're gonna look at the second thing over here, second topic. But before then, we will consider our focus is on the third one, the causal effect. Then what is causality? So we will talk about the concept of causality after having 10 minutes of break. Okay.
Well, firstly, I just learned Tuesday is something I checked. Wage. This, but you said this is wrong. Because this is something like
Oh yeah, then probably.
this is but
Yeah.
the question is not this.
Yeah, right. So if you do this, then the problem is when you, you can do this. Yeah, first of all, you can do this. However, the problem is you have to overlay this line on the scatter diagram. Yeah, scatter diagram of the data. The scatter diagram doesn't have education square. It has only education.
No, we generate the.
Yeah, right. So look at this. So in your data, you have education, and the wage, right? So you have data over here. So each point, you have just education instead of education square, right? So what you want to do is, you want to plot a quadratic line that is associated with this regression, right? So if you put this line over this, then this variable is different from this variable. So you are losing consistency between what you are doing over here and the scatter diagram. But if you put y at 2, just like I explained, and education, then you still have the same variable on the horizontal line, right?
But this is changed, which is not going to.
Yeah, this is y hat. Y hat is for our prediction for wage.
We cannot generate
That's what I ask you to generate y hat 2 using predict. Yeah. No, you can do this right after running regression, the first regression, and similarly you can generate y hat 2.
What is XB?
Yeah. XB is the option for fitted value.
So we just have XB.
Yeah. So the run regression first, say wage and education, and then you do predict y hat XB, and then you run another regression, wage, education, 2, and then you calculate y hat 2 XB. Then this is the fitted value from this regression. Yeah, immediately before this one, right?
Why we need to do this?
Because you want to draw the regression line from the first one, and then you want to draw another regression line that is coming from the second one, right? Yeah.
We don't need this to.
Oh, yeah, right. Yeah, you don't need this because for this straight line, you can have alternative way to do this.
Yeah.
Yeah.
But first, we do not have a favorable so we need to generate.
No. You can use this command to compute this one. However, this is easier way. Yeah. Yeah. Once you do this, you don't have to do this again.
Oh, yes.
Yeah.
It's right to place marginal effect. I don't want to use x plus 1. Is it right?
What is this one?
The marginal.
Marginal effect. Okay, so here education is still discrete, right? Then you have different left-hand side variable, but you have the same regressor, right? So you need to compute the difference of prediction between education and education plus 1, right? That is, yeah. That is, however, the left-hand side variable is log of wage, right? So your prediction has to be just wage instead of log of wage. Then the way you compute. So when you have log of wage, what is wage? Wage is e to the this whole thing, right? And then you can do the similar exercise. One time you put education, and then you have predicted wage, and then you do the similarly. You do this exercise similarly, but education plus 1, right? And then you take the difference. This is the right way. Yeah. Yeah. So this is inverse function of log. Yeah. So yeah, x when you have log, then if you have exp, then that becomes x. Yeah. So by doing this, you can get rid of log, but you need to have exp over here, exponent function. Another way to write this is e to the log of x is x. This is calculus.
So I can calculate this to calculate x plus 1 like this.
Yeah. Yeah.
And in the question 8, and I want to plot the residue, and should I calculate put the regressor line?
If it is not asked, then you don't have to.
It's
Yeah.
not
Correlated?
no, I mean the
Yeah. So if you want, this is just a residual. So if you put regression line over the diagram of residual, then the shape is going to be strange. Yeah.
and this question is at this 2 and this score is plus the larger one, and so which is means the effect is positive. And not the negative one. Because more the students and they have school. So is they have a positive effect.
You're talking about the correlation between Z. That is basically this one.
Yeah, that's
And the student ratio.
yes. Student ratio.
You're talking about student ratio. Yeah. It's almost time. So you have a question?
Question, can we just
Are they similar?
So this one is for residual and this one is for fitted value.
So they're
So
different.
they're different. So this one is computing E hat, this one, and this one is computing wage hat, wage hat. Yeah, yeah. This one,
We should construct this like to compare which regression model is better. Yeah.
for which problem?
Yeah, I wanted to, the last question is to discuss like all the models. So I wanted to fit like all the regression lines in one graph.
Oh, actually, there's no one particular answer for the last question.
Yeah,
So
so I should use this, right?
there are many different ways, so I cannot say which one is the best way.
Yeah, and about
Yeah.
the marginal effects, can I just take derivatives instead of like doing this x plus 1 thing?
Again, that is an approximation. So sometimes approximation can be reasonable, but not always. So evaluate the prediction at the x plus 1 and minus the prediction at x is the right way to do that. So that is the right way. So if you didn't know the right way, then you should do the approximation. But now you know the right way, so you should do the right way.
Yeah, okay. And about the regression line, we use QZ to do like
Yes,
this one.
yes.
And about the logarithm, what should we use?
For log,
Yeah,
actually I didn't ask you to.
I just wanted to construct it by myself
Yeah.
to see how it fits. And what should we use in this case? Or there is no
In that case, you have to put scatter diagram with modified data. So you cannot generate this line just using log of the left hand side of it for now. Yeah. Oh, actually, this is time. Okay, so let's look at this table once again, because this table is important to understand the concept of controlling for a new variable. So the first bullet point is districts with fewer English learners have a higher test score. Let's check if this is true. So districts with fewer English learners, then these two are districts with fewer English learners, and they have higher test scores. So for small class sizes, the test score seems to be okay. So 664 and 665, these numbers are bigger than these numbers. The test scores for larger English learners, right? So these two numbers are larger than these two numbers. How about the districts with larger class sizes? So these two are larger than these two. So the first bullet point is right. Districts with fewer English learners have higher test scores. So it looks like, so from this, it's pretty obvious that English learner, the proficiency of English language is one of the determinants of the test score. That's what this first bullet point is saying. And the second, districts with lower percent, so that is basically fewer English learners, have smaller class sizes. Let's see if this is right. So lower percent of English learners over here. What is class size? Okay, so we have 76. So the first category, we have 76 small class size, the districts of small class size, and 27, right? So for the first category, the ratio of districts with small class size is way bigger than the other case. For the second category, this ratio is still bigger, but not as much, but still bigger. For the third one, now the ratio of English learners is pretty larger than before. It's up to 23%. It's pretty large. The ratio is about the same, 54 and 50. And for those districts with largest percentage ratio, the percentage of English learners, now the ratio of student-teacher, the districts of larger class is even larger than the other case, right? So it is true that districts with lower percent English learner have smaller class sizes. And look at the last bullet point. Among districts with comparable percentage of English learners, which means we are supposed to look at each one of these rows, each one of these categories that are categorized by the percentage of English learners. The effect of class size is small, which means compared to this aggregated effect, the effect that ignores this additional variable. So the effect of class size for the first category is even negative, although this is statistically insignificant. The second category is 3.3, and the third category is 5.2, which is the largest, once we take into account the effect from the English proficiency, right? But the largest one is still smaller than this aggregate effect, compound effect, actually. This is called the compound effect because this measure observes partially the effect from this omitted variable. So that is why this estimated number is compound effect, right? So the last bullet point is also true. After we consider these additional variables, percentage of English learner, the estimated effect of class size seems to be way smaller than this compound effect. Yeah, so these three things are the important things that you have to learn from this table. So from this example, if omitted variable satisfies the two conditions for omitted variable bias, then OLS estimator in the regression omitting that variable is biased and inconsistent, which means here this is our OLS estimate excluding this important variable, and these are the estimated ones. So our OLS estimate seems to be very different from the more accurate effect. So our OLS estimate tend to be biased, and it is not consistent. So even if sample size is very large, our estimate is not going to be close to the true population parameter, the parameter that we are interested in. So here we reach to the same question. We had this regression equation. When we have data, we can estimate beta 1. And when we have data on Z, then we can still estimate beta 1. The problem is this beta 1 is different from this beta 1 when we estimate. This is the thing that we want to estimate. Then what is this beta 1? The definition is different. So another way to say this is when we run a regression, what is the parameter that we want to estimate? Precisely what is the thing that we want to estimate using the data? So the first one is the summary of data. That is not interesting. And the second one is we want to use our regression result for forecasting or prediction when we have time series. This can be done without considering causal effects. And the third, which is more important, we want to estimate the effect on the left-hand side variable when we change some variable on the right-hand side by policy. So we are interested in policy effect. Example of policy effect is this. Suppose some district choose to cut the class size by 2 students, then what is the effect of this policy on the student, on the test score? We want to estimate that kind of causal question. Okay? So then we need to examine the concept of causality. Causality concept itself is quite complicated. So in this course, we want to take a practical approach to defining causality. A causal effect is defined to be the effect measured in an ideal randomized controlled experiment. So instead of giving you a technical definition, let's look at this example of ideal randomized controlled experiment. This is an experiment. In our real life, we cannot run this kind of ideal experiment, but because we have brain, we can think about this ideal situation. We can imagine this ideal situation. Okay? So subjects all follow the treatment protocol. So what does that mean? Perfect compliance and no errors in reporting, etc. That is, we are going to have, we're going to assign subjects into 2 different groups randomly. So from a population, so here we have population, and then we select one individual, and then toss a coin. Depending on the coin result, we put it in one group or the other group. We have 2 different groups. One is treatment group, and the other one is a control group. We need to have control group to measure the effect from the treatment effect. So having control group is very important. If we assign all the individuals to one particular treatment group, then there's no difference. We cannot measure difference. We select randomly individuals to assign some of them to the control group and the other to the treatment group, and then we run experiment. We put some new medication on the treatment group, and then a few weeks later we can see the difference of these 2 individuals. Then that is the result. That is the effect of the treatment. And the treatment is assigned as part of the experiment, which means subjects don't have freedom to choose the group. They don't have freedom to switch from treatment group to control group, or from control group to the treatment group. Once they are assigned to one of those groups, then they have to stay there. That is one of the requirements. But in real world, a rich family can go to the, The rich family can go to the school district with lower student-teacher ratio, right? So subjects have freedom to choose the thing that they like, right? If this kind of thing happened, then randomization failed. So in many cases, we cannot have ideal situation. But here, these are ideal randomized controlled experiment. So when it comes to the class size example, we can imagine an ideal randomized controlled experiment for measuring the effect of test score of reducing student-teacher ratio. What kind of experiment can we do that? In that experiment, students would be randomly assigned to a class. And those classes have different sizes. Because they are randomly assigned, all students for each different class size should have same characteristics. In other words, they are distributed independently of the treatment. In this case, the treatment is student-teacher ratio, which means the error is orthogonal to the regressor, the treatment. So once we have this condition satisfied, then we can say that the first condition of linear least square assumption holds in a randomized control experiment. Then we're going to have consistent estimator. But in economic data analysis, we are going to have observational data instead of data from experiment. The treatment is not randomly assigned. So in this case, think about the percentage of English learners in a district. Plausibly, this satisfies the two criteria for omitted variable bias. When we define Z as the percentage of English learners, then the percentage of English learner will determine the test score partially. So this is part of the prediction error. And as we have discussed, this ratio, the percentage of English learner, must be correlated with our regressor. In this case, that is student-teacher ratio. Because if we admit that this assumption is reasonable, the assumption is, migration community, immigrant community are less affluent, then the school districts with more English learners tend to have smaller resource for the school budget, right? In that case, then the student-teacher ratio will be higher for those school districts. So we can argue that the correlation between the included regressor and this additional omitted variable is not uncorrelated. So the correlation is non-zero. Then this implies that the first condition of least square assumption is violated. So we cannot have consistent estimator. So when we have randomization and the control group, then any difference between the treatment group and control groups can be interpreted as a causal effect. So in our example, by looking at similar districts in terms of this new variable, we can eliminate all the effect from the ratio of English learners. And then for each different categories, we can measure the effect of class size on the test score, as we have seen before. So this is one way to control for the effect from percentage of English learner when we estimating the effect of student-teacher ratio. But this is not the only way to do that. Actually, there are three ways to overcome the omitted variable bias. The first one is, if possible, we can run a randomized control experiment. But this one is, again, this is really ideal, and this solution to omitted variable bias is rarely feasible in real world. We are not supposed to dictate where those families live randomly, right? So in many real situations, the first solution is not feasible. This is only ideal solution. And the second one, we already discussed about the second solution. This solution is called cross-tabulation approach. For this approach, we categorize the sample across different level of percentage of English learners, and then for each group, we measure the effect of class size on the test score. Then the problem is, basically, this second approach can be done approximately as before. So let's go back to the previous table. So what we did in this table is basically to implement the second approach in an approximate way. So 1.9%, everything below 1.9%. This can be 1.8%, 1.7%, right? So we collect all different percentage ratio under this first category. And the second category also collect many different categories as well. And the third category, similarly, right? So we can have finer classification than just these four categories. The finer, the better. And as long as you have this rough approximation, you will still have compound effect. We cannot argue that this is really the effect of the student-teacher ratio on the score, test score. Because even within this group, there are variation in terms of percentage of English learners, right? So this number doesn't capture the effect of class size on the test score in an exact way. If you want to have better estimate, then we need to classify percentage of English learners in a finer way. Then we will have so many categories. We will have a lot more categories. Then, here, what is the sample size? In the beginning, sample size was this number, 238 plus 100, so roughly 400, right? Roughly 400. If we have so many classifications, then for each category, we will have very small sample size, right? So that is the problem of this approach, the approach of tabulation. So cross-tabulation approach. This is one solution, but very soon you will run out of the data. For each classification, you will have only small sample. And then your estimate for the causal effect is going to be captured imprecisely because you have small sample, right? And the last one, we can use a regression where omitted variable is no longer omitted. So go out and collect data on this omitted variable. In this example, that is a percentage of English learner. So once you collect this additional information, then just include it as an additional regressor in a multiple regression. This is the last solution. But the problem is, if it is possible, then this variable is not omitted variable anymore, right? So this is one possible way to overcome omitted variable bias, but I would say even this last one is not always feasible. If you can collect the information, then that is not omitted variable anymore, right? We will discuss about the situation where we cannot collect this additional variable in practice later. But today, let's think about this third solution. So previously, we had only X1. Back in the example, X1 was student-teacher ratio, and X2 is the percentage of English learner, right? But using this more general notation, we can apply this mathematical expression for wider range of applications, not just test score. So more generally, y is called the dependent variable or left-hand side variable, and x1, x2 are the two independent variables or regressors, right-hand side variables as well. And we put sub I to indicate that these variables are describing ith observation in the data. So sometimes we don't have I of the variables. Then this y, x1, and x2 are generic notation for these three variables. Sometimes we want to emphasize that those variables belong to ith observation, then we put this subscript I. But basically these are measuring the same thing for particular individual. Beta not. This is an unknown parameter for intercept of this equation, and beta 1 captures effect on y when we change the first variable, holding x2 constant. So here this is important. Beta 1 measures the effect of x1 on y when x2 stays the same. And x2, similarly, x2 measures effect of change in x2 on y when x1 stays the same. We have to keep x1 the same. So basically, so in this way, we can separate out effects from two different variables on the left-hand side variable. We can decompose these two effects. And UI is again the regression error. So even after including this additional variable, there can be, possibly, almost always, there must be more variables that can be regarded as determinant of this left-hand side variable. But as long as they are not correlated with x1 and x2, then that is fine. So how to interpret beta 1 and beta 2? Once again, so consider we change x1 by some increment, delta x1, but we don't change x2 at all. Then before we change, the population regression line looks like this, without having this error term. Error term is not included in the population regression line. This is line, just line, without having any error. And then population regression line, after we change the value of x by this increment, the population regression line is going to be this. There must be the change. And then the difference can be captured by beta 1 times the increment in the x variable. So beta 1 is nothing but the ratio of increment in y and to the increment of x1, holding x2 constant. Similarly for beta 2, right? And beta naught is a predicted value of y when both x1 and x2 are 0. But in many cases, intercept is meaningless. Intercept can be meaningful only when these variables, so our data contains 0 inside our sample range. For example, one of your tutorial exercise is about the relationship between wage and how tall you are, right? Yeah, you had this one. So if you put 0 over here, then you're going to predict expected wage for those people with height of 0, right? But we don't have such person in this world, right? Everybody has some positive height. So in that exercise, our data never contains 0 value inside of its range, right? Then if that is our exercise, then predicting left-hand side variable at value of 0 doesn't make sense. So intercept is meaningless in many situations. But not always. For some examples, we can predict value of y by plugging 0 on the right-hand side variables. Because we could have some variables that can be negative and positive at the same time. Then what is definition of OLS estimator? So for one individual, look at this. Yi is the random variable on the left-hand side left-hand side. This is the random variable that we want to predict. How do we predict? If we didn't have any additional information about the individual I, then we will choose just one number, right? So think about, imagine that we don't have x1 and x2. We don't have x1 and x2. We have only b0. Then by selecting b0, we can predict the left-hand side variable. For this problem, the solution for b0 was sample average, right? Okay, so think about, let me repeat it again. So for now, for the moment, let's assume that we don't have x1 and x2. x1 and x2. We only have x0. And by choosing x0, we want to predict the left-hand side variable for individual I, but not just for individual I. We want to do well on average. Because we want to do well on average in this prediction problem, we measure our mistake by this difference. And this difference can be negative and positive, so we want to have positive measure. That's why we square it, so that our error is measured by some positive number. And we are interested in the level of mistake across all individual in the sample. That's why we sum. Actually, after summing them up, we can divide it by n. But the problem is the minimization of our error. So we don't have to divide the sum by n. Dividing it or not will give the same solution. So in terms of the solution, we don't need to rescale this sum. So if we didn't have x1 and x2, the solution to this problem is sample average of y. Now, we have a better environment, better situation. That is, for this individual, we have more information, x1 and x2, possibly more than just two. We could have third and fourth, we could have many variables. So using this information, we want to predict the left-hand side variable. We assume that the population regression line is a linear function. So that's why we put this linear function. Actually, linear in the parameters, not in variable. And then we want to minimize our mistake square across all individuals by choosing, now we have three parameters, B0, B1, and B2. You can do this if you know some calculus. Take derivative of this control variable, this objective function with respect to our control variables, and set it equal to 0, then we will have three equations to be solved simultaneously. And then the solution to this minimization problem turns out to be a definition for the OLS estimator. So this minimization problem can be solved using calculus. There's there's a closed form solution. And those solutions are OLS estimators for these population parameters. So here, let's go back to California test score data. Previously, when we include only student-teacher ratio, this was the estimated regression equation. Now, we include additional variable that we didn't include previously. So when we do this, this additional variable was omitted. And we learned that there's a good reason that this omitted variable can cause bias on this slope parameter, on the OLS estimator. Not only this, but also the intercept as well. Now, let's suppose that we go out and collect additional information on the English learners, the percentage of English learners. Then we include this variable over here. Then we run this estimation exercise again. right? Now, the measured effect of student-teacher ratio on the test score seems to be smaller than before, right? So this observation, this finding is consistent to our discussion about the table where we had 4 different categories for percentage of English learners, right? In that table, for each category, the effect was smaller than the aggregate compound effect, right? So the way to run this regression with multiple regressors is this. We are using the same stata command and put the left-hand side variable first and then list the right-hand side variables right after the left-hand side variable. After comma, we put robust because we want to have robust standard errors. Then after you write this and then hit the enter key, then you will see this computation results. And here, these first columns are estimate for the coefficient. And this result can be written in this way in an equation form. So when you are asked to write down the estimated regression equation, then this is a part of your answer. Usually, you need to give standard errors right after these estimates in parentheses. And also, usually, you have to give some measures of goodness fit. So now, let's think about measures of fit for multiple regression. The discussion is going to be parallel to our discussion for the simple linear regression, the regression with only one variable. Actual value of y can be decomposed into 2 parts. The part that we can explain, we can predict, and the part that we cannot explain by our regression line. So y hat is sum of predicted value of y and the residual of it, right? So using this decomposition, we're going to build up the definition of R square. Before doing that, what is this standard error of regression? We can compute standard error of regression. That is just standard deviation of residual. This residual is the difference between fitted value and actual value. So SER is the version of standard deviation that corrects a degree of freedom. And root mean square error. So today, early in this morning, I fixed a typo over here. So if you printed out the lecture note before this morning, then you might have some typo. Please fix this typo. Conceptually, this is the same as standard error of regression, but this is without a degree of freedom correction. Degree of freedom increases as we have larger sample. So for large sample, there's no difference. Actually, that's why when we compute this regression using stata, the stata only report root mean squared error, 14.464, right? It doesn't report standard error of regression separately. Because when sample size is large, there's no difference. They're going to be very close to each other. And R square, this is a fraction of variance of y explained by x. And we will see adjusted R square. R square doesn't control, just R square ignore the degree of freedom. But R bar square will consider the effect from a degree of freedom. The problem is this. R square is an increasing function of the number of variables. Whenever you add more variables in your regression analysis, you will have bigger R square, right? So R square suggests that you should use more complicated model, right? So what this adjust R square or R bar square is doing is it penalizes the complexity of the model. So let me give you a definition for each one of these measure of fit. So standard error of regression is defined in this way. Just this is definition of standard deviation of residual, right? So here, denominator, you have number of parameters over here. K is the number of random regressors, and you have to take into account the constant when you include the constant on the right-hand side. But root mean square error doesn't consider the number of parameters here. So the way to compute these two things are very similar. Only difference is this, the denominator inside of the square root. And R square, the definition of R square for multiple regression is exactly the same as before. This is exactly the same as before. This is a review of the definition. But like I said, R square always increases when you add another regressor. This is a problem because it suggests that you have to use more complicated model. You know, if things are equal, you should choose simpler model. So R bar square is invented to solve this problem, and R bar square is defined in this way. So as you increase the number of parameters over here, then it will lower the value of the R bar square. In this way, you can penalize the complexity of the regression equation. So R bar square is always smaller than just R square, but when sample size is large, then these two are going to be very similar with each other. So if n is, think about this situation. N goes to infinity, then the numerator and denominator both approach to infinity at the same speed, right? So this ratio is going to be 1. Then it becomes the definition of R square, right? Okay, so test score example. Previously, when we consider only student-teacher ratio, R square was 0.05, which is close to 0, which means this variable doesn't explain the test score in an effective way. Okay, now when we include percentage of English learner in a district, we have larger R square, which is much, much larger than this. That implies that this variable, actually that suggests that this variable have to be included in our analysis. So, and also the standard error of regression shrinks. So the smaller, the better. When we are using this measure for goodness of fit, standard error for the standard error of regression, the smaller the better. But for R square, the larger the better. R square takes value between 0 and 1. If R square is 0, then regressor doesn't have any explanation power on the left-hand side variable. If R square is 1, then our regressor has perfect prediction power, which is a deterministic function. The left-hand side variable is completely determined by the right-hand side variable. Mostly R square is between 0 and 1, excluding the boundary point. But this is standard error. The unit for the standard error is the same for the unit for the test score. So this is something that you have to keep in mind. Which means for different data, the way we interpret R square is similar, but the way we interpret the magnitude of the standard error of regression can be very different. In this exercise, R square is similar to R bar square. That is because sample size is large. In this exercise, the sample size is 400 something. If I remember correctly, 420 something, but anyway, order of that. Then question is how to choose a variable. You know, if you look at the actual data set, you can observe a few more variables that you might be interested in when you explain the left-hand side variable. Then should we maximize R bar square? This is another question. Should we choose a set of variables in such a way that we maximize goodness of fit measured by R square? Is this the right way to choose the model? Actually, this is a quite difficult problem. The choice of model. Modeling choice is a very difficult problem. So next chapter, we're going to discuss about how to choose a variable for regression analysis. This is not our topic today. So let me review least squares assumptions for multiple regression. These assumptions are almost identical to the three assumptions for least square regression when we have single regression. So the first one is comparable to the first condition that we have seen. Only difference is we have many variables. And second, we assume that data are IID from some population distribution. So this is identical to the previous one, but only difference is, again, we have many regressors. And large outliers are unlikely. No, this is exactly the same as before, except the number of regressors. Only additional thing is there's no perfect multi-collinearity. So I'm going to talk about perfect multi-collinearity. Let me skip this because this explanation is kind of repetition that we already seen. Assumption 1 is important because without having this assumption 1, that means we have omitted variable bias. So then we cannot have consistent and unbiased estimator. So we will discuss in more detail about the situation where this condition is violated. Assumption 2, the IID assumption. This is automatically satisfied if data are collected by simple random sampling. So usually when we have cross-sectional data, we don't need to worry about the second assumption. Large outliers, to detect the outliers, the existence of outlier, the best way is to check your data, plot your data using scatter diagram, and then see whether there are some crazy values. And if there are crazy values, then you look into your data set further, then see whether there's a coding error or things like that. If there's a coding error or typo, then you exclude those individuals, because including some individuals with errors that can be actually very dangerous. That can shift the magnitude of OLS estimate quite a lot. And number 4, perfect multi-collinearity. So actually, in practice, this is not a problem. The problem is, so what is perfect multi-collinearity? You have many variables on the right-hand side, and if one variable is perfectly explained by some other variables in a linear function, then we say that we have perfect multi-collinearity. One of the variables is redundant, right? If you have this kind of situation, numerically we cannot find OLS estimator. What Stata does in this case is automatically drops one of the probability variables. So problem is automatically solved. So under these assumptions, OLS estimators are unbiased for all parameters. OLS estimators are unbiased. And the variance of OLS estimator is inversely proportional to the sample size, which means if we have larger sample, then our estimate is going to be more precise. And we can show that when sample size is large, the same definition of the T ratio is approximately distributed as a standard normal distribution. So we can use this result for hypothesis testing and constructing confidence interval, right? So when we have this null hypothesis, then we can make a decision following exactly the same decision rule, right? Now, next week, we will come back to this point. We're going to discuss about perfect multicollinearity and imperfect multicollinearity. And exam will cover this chapter, right? So exam will cover multicollinearity too. All right, have a nice week, and I will see you next week.
Two quick questions.
Yeah?
So, for question 2 for the
Actually, I don't remember what the question two was.
I just asked you when you do your why would you regression you when you add your before we don't ask the how much schedule already. Because question 3 you asked us to test the schedule. And so in the question 2 when you do regression when you add your or you don't need to.
Yeah, so if you want to compute robust standard error, the only thing that you need to do is just to put robust after
I know.
after the regression.
Yeah, so I mean like we need to, because it's like after the testing it's homoscedasticity, so we don't need to do it. So in the question 2 before the question 3 or 4, you will need to add a robot.
Actually, you don't have to, but it is good practice.
If we
to,
add it.
Yeah,
Okay.
yeah, because if you calculate robust standard error, then you wouldn't lose anything, even if the error is homoscedastic.
Yeah.
Okay?
Okay. And one more is when we do the law, how can we do it? So we generate a new.
Yeah, I think we need to go out. So let me check if
Alan, how's it going, man? Yeah,
Not
yeah,
bad at all.
Yep.
USB drive.
You bet. I'll sort it out and what's the best one?
can catch up next
If
week.
you want to just get it off your next week, or if you want to
I
just,
can get it off on Friday.
yeah, okay. I'll be around.
Yeah,
Good on you, man. No
Thank
worries.
you for everything. And,
Oh, my pleasure, mate. I'm happy to help out as much as I can, you know. Like it's, yeah. Now, did anyone get in touch with you? I flicked you on your email on to the.
yeah, but then again, I
He
do
will.
work, so the phone's going
Ah, okay.
yeah, so just get it, run out of work, get
Yeah, yeah,
relax
yeah.
work.
Yeah, no worries.
You know yourself, of course. Keep in touch to...
Please do. Yeah, let me know how you're going and if there's anything I can
I
kind
was
of do.
speaking to Paul about the tutorial with the Simon point.
Yep.
So I don't know the practice work and all that. So after like I clicked over on head got sent back
Yep.
and it was very kind of all maths side of it.
Yep. Yep.
When it comes to kind of drawing the distinction between maths and the English side, I get lost.
Yeah, okay.
And that's what I'm trying to that's hard to put it on.
Okay.
So I'm gonna have a stab at section 5.
Yep. Well, look, make sure you go through the 1 to 4 stuff and get as much feedback as you can and really, yeah, okay then.
If you went to 1 4, I'd say that's 29 out of 35, isn't it? The exams are there and where it
Yeah,
was.
perfect. That's great.
But 5 questions got wrong were on the written answers. So on the part 5 is all written answers.
Yep.
So that's where I'm going like it's going to be if I ask what you say ideas, let me know.
Yep.
I'll keep you in the loop as well.
Definitely do, man. Let me know, and if there's anything we can do to help us, we really want it. So, good on you, man. Hey, mate.
Spinal nerves.
Can we do it afterwards, please? Yeah, I just need to get ready now, make sure I'm ready to kind of go. So, but yep,